Welcome to this part of the RC analysis. In the previous video, I have discussed an alternative approach for some of the questions there. Now I will be discussing about the proof of that alternative approach. So what I said was that at t is equal to 0, if there is a parallel combination of capacitance and resistance, we can consider it to be a single capacitance, and in case of series combination, you can consider it to be a single resistance. And at t is equal to infinite, you can consider this thing as a single resistance and this series combination as a single capacitance. We'll look into that proof in some time. Before that, I want you to know what is a step input. Step input is a function in which the values of the function will be 0 at time instances lesser than 0, and for time instances greater than or equal to 0, it has some constant value. Here I have assumed it to be V1 volts. Okay, this is the step input. Now looking into a simple sine wave with say f1 frequency, this is a simple sine wave with f1 frequency. If you try to increase the frequency of this sine wave to say f2, here I have assumed f2 greater than f1, you see there are multiple waves in single time period, right? Assume this thing as t1 time period, and as you keep on increasing the frequency of this sine wave, the gap between two ripples get shorter and shorter, and also the number of sine waves in a single time period keeps on increasing. What if you increase the frequency of the sine wave till it reaches infinite? This thing becomes a step input. As you can see, this is at t is equal to time instances lesser than 0, this thing will be 0, and suddenly when t is equal to 0, when you increase the frequency till infinite, this thing is just this, and suddenly you stop it to 0 and it goes constant, right? So at t is equal to 0, this thing is something special. So in this case, if you see closer at this time instant when t is equal to 0, this thing is just same as this one. Okay, so what we infer from this derivation is that for step input at t is equal to 0, the frequency of the input signal reaches infinite. Before and after that point, the frequencies are just 0. We can assume it to be DC 0 and DC high. Okay, so if you consider a capacitance, the impedance of the capacitance is given by Zc, which is equal to 1 by Sc, and the value of S is J 2 pi f. And if you substitute the value of f at t is equal to 0, which is infinite here, 1 by infinite becomes 0, right? And at t is equal to infinite, step input is just a DC signal of specific voltage. Here it is V1 volts. A DC signal has frequency component of 0 hertz. Okay, so if you substitute the value of frequency here in the impedance formula, you get impedance of the capacitance to be infinite. And if you substitute these two values in those equations or the circuit, you will get the equivalent circuits here. So at t is equal to 0, the impedance of capacitance becomes 0, right? So this thing is closely equal to a short circuit. So if there are two resistors, say R1 and R2, in which R1 is much greater than R2, and they are in parallel combination, the equivalent will be somewhat equal to R2, right? And in series combination, if this is the case, this thing will be equal to R1, right? We follow the same rule here. So consider this C1 as an impedance whose value is much lesser because it is equal to 0, right? So much lesser than the second value. So this thing will become equivalent to a single capacitance. And here if you see, C is much smaller when compared to R, right? In series combination, this thing will be just a single resistance. And at t is equal to infinite, the Zc is equal to infinite. Zc is infinite, right? Okay, so C is much greater than resistance. So this equivalent will be a single resistance, and here C is much greater than resistance, so this thing's equivalent will be a single capacitance. Okay, I hope you understood this proof of the alternative approach that I taught you in previous video. Thank you for watching this video. I'll meet you guys with a new video in the upcoming days.